Wonderful. Well, hello everybody. Thank you very much for coming along, and hello everybody else who's online. My name is Ian Robinson. I'm a specialist solutions architect for data and analytics at AWS. And in this session, I'm going to be covering serverless big data analytics with Amazon Athena and QuickSight. I've actually thrown in a couple of other services as well, so we'll have a brief look at Glue, and I'm also using S3. I'm then running the follow-up session where we'll do a deeper dive into Glue. So we'll just have a quick look at Glue in this session, deeper dive in the next session. I thought I'd frame this at the outset with a brief discussion of Agile Analytics. So you've probably all seen a diagram like this in the past, probably quite familiar with this. You know, kind of traditional data pipeline. We're collecting data, storing it, doing some analysis, potentially doing some transformations to a more query-optimized model, performing some aggregations, doing some analysis, consuming that data. Yeah, very traditional data pipeline. Now, in the past, the time it takes to complete this pipeline could be in the order of days or even weeks. We have to identify the data, and then we have to acquire that data. We might have to think about procuring or provisioning compute resource or storage, or actually acquiring some infrastructure, some hardware, and so on. So the time it takes to go from an idea to insight can be in the order of days or weeks. That's pretty slow, pretty burdensome. So ideally, what our end users would like is to be able to reduce these cycle times, to be able to run lots and lots of these data pipelines one after another, or to even interleave them. Right? This is a more agile approach to developing an analytics capability. If we can reduce those cycle times, it gives us a lot more freedom in terms of being able to experiment with our data. We can throw things together, bring in existing sources of data that we might have acquired, choose an appropriate technology, begin some analysis, begin to experiment. If that experiment looks fruitful, we can continue to invest in it. But if it looks as though it's leading to a dead end, then, well, we just want to get rid of it, kill it, cancel it, and stop paying for any of the resources that we're using to do that processing. And with this kind of setup as well, we can react far more quickly. You know, if the market, if competitors force us to reevaluate our understanding of our data, to conduct fresh analyses, and so on. Again, with this more kind of agile approach to being able to reduce these cycle times, go from idea to insight, we can react far more quickly, we can be far more agile, far more powerful with regards to the ways in which we process our data. So what I'm going to show today is a way in which we compose several of the AWS services in order to build the foundations for an agile analytics platform. And in this, we're going to take advantage of predominantly serverless services, and the ones where we don't really have to think about capacity planning or sizing infrastructure or provisioning that infrastructure. These are the kind of services where AWS is taking on all of those responsibilities. It allows you to focus on the stuff that's really important to you, whether that's transforming your data or actually querying the data or generating visualizations on top of it. You get to focus on all of that and let us worry about standing up the infrastructure and doing the processing in the background on your behalf. So this is the kind of setup that we're going to look at today. We're going to take some raw data that's stored in S3 in the simple object service. I mean, in this case, we've actually got some data from the New York transportation system. So we've got some taxi data, some limo data, and some data from Uber. Yeah, so 3 different data sets which we've already acquired and we're storing in S3. So that's our raw data up here. We're then going to catalog that data. So we'll catalog it, means that at some point in the future, it's going to be very easy to discover that data, find out where it resides, what formats it's in, what schema is applicable to that data. So we'll catalog it. And then we'll do some transformations on that data. Right? So we're going to build a model, an analytics model, that is optimized for a set of queries around this transportation data. So we're going to take 3 different sources with slightly different fields, slightly different schemas, and we're going to transform it and write the output of those transformations to another bucket in S3. So we're going to change the schema slightly, kind of canonicalize all of the column names, but we're actually also going to transform the data format. So our raw data is CSV, our output data is going to be PARQUET, a kind of columnar query-optimized format for large aggregations, large kind of large-scale analytics. So once we've done that, once we've got our canonical data, or our canonical model in S3, we're then going to start querying it using Athena. And Athena is our managed or serverless interactive SQL service. It allows you to write SQL against data at rest in S3. No need to spin up any other infrastructure. You can just start writing SQL against that data in S3. You could actually write it against the raw data, but we'll have actually gone through some process of canonicalizing it, transforming it, optimizing it for our analysis purposes. So we'll see some SQL queries against this data. And then on top of that, we're going to put Amazon QuickSight, which is another managed service that gives you a BI or a visualization tool in the browser. You can create dashboards, and you can share those dashboards with your users within your organization. Okay. So let's go through some of these moving parts in a bit more detail. I mentioned that we're going to catalog our data, and we're going to apply some transformations to it. Now, traditionally, we do those transformations either using a third-party tool, such as Talend, or we would spin up something like EMR, a managed Hadoop cluster, perhaps install Spark, and use that to apply some transformations to our data, calculate some aggregations, transform the format, and so on. What we're going to use is a new service from AWS called Glue. It's a service that was announced re:Invent last year and was made generally available in the US a couple of months ago. And we'll talk a little later, or at the end of this session, about release dates elsewhere. Okay. So we're going to use that. It's a managed or a serverless ETL capability. And it also exposes a highly available Hive Metastore compatible data catalog. So we're going to use these two different parts of Glue in order to catalog and transform our data. So this is Glue. Glue simply has three core capabilities. It has a data catalog. So as I mentioned, this is a highly available Hive Metastore compatible catalog that stores metadata describing all of your sources of data in AWS. Now, we've added some additional features to that catalog, some additional APIs. We've added crawlers that will actually go discovering data within your estate and uploading that metadata into the catalog. Once that data is in the catalog, once that metadata is in the catalog, describing your sources of data, describing the schemas and so on, that metadata can be consumed by a number of other services that we expose. So the table definitions that are stored in the catalog can be used by Athena, for example, and that's what we'll be doing today. Athena can consume those table definitions and allows us to write SQL against the data wherever it resides. We can use it in Redshift Spectrum. We can use the catalog in EMR. We can use Spark and Hive in EMR and point that at our catalog as well. So the very same table definitions in the catalog we can reuse via several services, all pointed at the same sources of underlying data. So that's one thing that Glue does very well. The other two things are really around ETL jobs. Glue will allow you to compose transformations. Given a source and a target from the catalog, create for me a transformation. It will take data from the source, transform it, and push it into the target. If we create a transformation through Glue, Glue will actually, behind the scenes, create for us some code, some Python code that addresses Spark, so it's PySpark code. We can open up that code in our own IDE or in the browser, and we can further modify it, further enrich it, and so on. So we can actually modify the scripts that we then want Glue to execute. And the last thing that Glue is responsible for is job execution itself. We can specify the schedule when we want these jobs executed, whether it's on a periodic basis, or whether it's in reaction to certain events. You know, data lands in S3. I want to use that event as the trigger for a Glue job. We can specify all of that in Glue, and then we leave Glue to be responsible for actually scheduling and executing those transformations on our behalf. So what I've done prior to this session is actually take two of those sources of data, the taxi data and the limo data, and I've already run some Glue jobs on top of them to transform them into a canonical model and to transform the format into PARQUET. All right. So with those two sources of data, we had just over 1.5 gigs of taxi data and 220 megs of limo data. So this is not a huge data set. I think this is actually data only covering a few months from 2016. But in applying those transformations and converting to PARQUET, to this query-optimized columnar format, we've actually significantly reduced the data set sizes. So we've gone down from just over 1.5 gig to just under 100 meg, from 220 meg down to just 18 meg. So we've got much smaller files in our canonical store on S3. Again, I'll talk a little later on about these columnar formats in more detail and about some of the benefits that they offer us. So this leaves us with the Uber data that we want to transform and push into that canonical model. So what we're going to do here is actually look at Glue, look at the Glue console. I've just got to mirror my... Can we see that okay? Good. All right, so this is Glue's console. And like a lot of services, Glue also exposes an API, so we can consume it via the command line or via Java SDK. But we're going to do everything today through the console. So you can see on the left-hand side, we've effectively divided it up between those two big capabilities, the data catalog and the ETL. And within the catalog, we have this concept of databases. And a database is simply a collection of table definitions. They don't have to be relational databases and relational tables. It's just effectively a metaphor for describing sources of data. These are the databases that I've currently cataloged in my account. One of them I'll be using in my next demo, a couple of them that we're using in this. The NYC Transportation database is our raw data. NYC Transportation Canonical is our target, is that canonical model that we're building. So this is the NYC Transportation database. It includes 3 different sources of data. Data for those limo rides, data for taxis, and data for Uber. And we can actually see that the underlying data is stored in an S3 bucket. It's not an S3 bucket I can control. So this is actually cross-account access in order to access that data. So we've got these 3 sources of data here. Then I have a second database, which is my canonical database. I've not actually created a definition for this yet. In a little while, when we look at Athena, the first thing I'm going to do is actually create a definition, a table definition for Athena so that we can start querying it. Just trying to think what I need to do here and now. I think this section, I was simply going to review what's available in Glue. Okay, that's good. All right, so we're using Glue in a minute to actually do some additional transformation on that Uber data to get it into the canonical model. And we'll also be running a crawler, one of these little things that can go discovering sources of data, and that will create a table definition that we can start querying through Athena. So this brings us to Athena. Athena is our interactive query service. You can think of it as serverless or managed SQL queries. Instead of having to worry about standing up a data warehouse, Redshift, or having to provision an EMR cluster and install Presto or Spark, all you really want to concentrate on is writing SQL against data at rest in S3. And that's exactly what Athena allows you to do. So there's no infrastructure, no administration on your behalf. We're just maintaining a warm pool of instances that become available to you the moment you execute a query. So there's not even any spin-up time. The moment you execute a query, we start running it. We start executing it. Because it's a managed service, and we're constantly adding features to all of our services, the moment those features become available within Athena, they become available to you. So over the last few months, we've added the ability to be able to read encrypted data in S3, and we've added the ability to read several different file formats. So we've released supporting quite a wide range of file formats, and over time we're adding more and more file formats that we support. So several extensibility mechanisms. It's very easy to use Athena. We're going to use it again through the browser, through the console. So it gives you a very simple SQL editor-like experience. But it also exposes a JDBC endpoint, so you can connect your own SQL client to it if you want. And we also expose endpoints that allow you to control and query Athena by way of our APIs and our SDKs. So the process for querying data in Athena, if you haven't already created a database and a table definition, is, well, we need to do that. So you can do that in the console. You can create some Hive-like DDL to describe your external table definition. And all we're doing is creating metadata that describes the data. That's the only thing that's being stored in the catalog. So we can do that in the console. If we prefer, there's a little wizard that we can walk through that will allow us to create a table definition. Or, and this is my preferred approach now, we can use Glue and Glue's ability to crawl sources of data to create an external table definition, and then we can consume that from Athena. Once that's done, we start querying. A couple of other things just to mention about Athena. It's highly available. So we're maintaining this warm pool of server instances across availability zones. We expose an endpoint to you. They're the only things that you know about. Well, the endpoint's the only thing that you really know about. When you execute a query, we will choose appropriate resource in an availability zone in order to service that query. And because Athena is designed to query data in S3, well, S3 provides very, very strong high availability guarantees, 11 nines of durability. So all the objects that are written to S3 are replicated across the availability zones within that region. So we've got very, very high availability or durability guarantees for your data. So the benefits here, we don't actually need to load data. Once it's in S3, it's available for querying. Athena allows us to query data in its raw format. So if you're landing data as CSV or as JSON, as we have in our raw bucket, we can actually query that in its raw state. My preference is to convert that to a query optimized format. If we're regularly running large queries over the same body of data, then we can enormously improve latencies, reduce latencies and reduce costs by converting to a query optimized format. But that's not absolutely necessary. So you've got JSON, you've got CSV, you can go query it the moment it's there in S3. So in that respect, there's no ETL absolutely necessary. When we start querying your data, we'll start streaming the results back to the client. Okay, so you're not having to wait for us to generate the entire result set, which for an analytics-like query might be quite a large result set. Instead, we'll start streaming those results back to the client as soon as we start generating the first result. But we'll also put the entire result set to another location in S3 that you can control. Under the hood, Athena is using Presto. So Presto is an open source, distributed in-memory SQL engine. Okay? Now you can kind of reproduce the Athena-like experience by standing up Presto on EMR. But if you were to do that, you would have to think about sizing your EMR cluster, choosing the appropriate instance types, and so on, and maintaining its availability. We're doing all of that on your behalf. So we're maintaining a large fleet of warm Presto instances. But this is the technology that we're using under the hood. And then for creating those external table definitions, we're using Hive DDL. So again, a well-understood, familiar technology for describing table structures over external sources of data. Presto has its own ANSI SQL dialect. This has support for complex joins, so we can join tables in our Athena queries. It allows for nested queries, for windowed functions, so we could query over windowed data. Supports complex data types, so arrays and structs. And importantly, it also allows us to partition our data. So by partitioning data, we effectively supply in our table definition one or more partitioning keys. Right? So we're saying that our data in S3 is laid out perhaps month by month in different folders. All the data for this month will go in one folder, all the data for last month will go in another, and we might specify month as a partitioning key in our table definition. If we do that, and then if in our SQL queries we use a predicate aware clause that includes that partitioning key, then the query itself will only go and look at the data that's absolutely necessary for resolving that query. We can exclude all the partitions that don't immediately apply. So this is supported in Presto and it's supported in Athena. And it's a very, very efficient, a very, very useful way, again, of reducing latencies and, as we'll see, also reducing costs if we're choosing to use Athena. So I mentioned the multiple different data formats. Very simple ones, CSV, TSV. We can supply custom delimiters. We already have classifiers for Apache web logs, for CloudTrail logs. Very recently, I think within the last week or so, we introduced support for log/grok expressions. I don't know if you're familiar with grok. It's a nice way of composing regular expressions, building up composed regular expressions. So if you've got your own proprietary text-based file format, you can write a Grok expression that can parse that and generate schema and a table definition based on those Grok expressions. We also support JSON, both simple JSON structures and nested JSON structures, and Avro. And we support 2 columnar formats, PARQUET and ORC. Athena can also read compressed files. So again, it's really good practice when you're querying data at rest in S3 to have reasonably large objects, to compress those objects, and potentially to use a query-optimized format. Athena can read snappy, zlib, gzip, LZO compressed objects in S3. And as I mentioned earlier, we've introduced a feature whereby it can read encrypted data at rest in S3. What else to say here? It's fast. I mean, it's designed as an interactive query service. You might be familiar with other kind of MapReduce technologies where it may be that you end up waiting many minutes or even hours for that job to complete. And very often that's because those jobs are executed serially. We have to do the map, and then the reduce, then the next map, then the next reduce, and we have to wait for each of these stages to complete. Presto actually has a far more interesting model. It creates a directed acyclic graph of all the steps involved in executing a query. So it can actually pipeline steps. It can actually start a subsequent step even while an earlier one is underway. So this can significantly reduce the query execution times. So we're taking advantage of that in Athena. This is the important stuff. How do we charge for it? How much does it cost? This is a serverless offering. So you're not having to stand up any infrastructure. You're not having to pay on a per server basis. Instead, with Athena, we're charging on a per query basis. And the costs are $5 per terabyte of data scanned in order to compute your result set. All right? Now, if you're generating external table definitions through Athena using that Hive DDL, that's free. If a query fails, that also is free. If you cancel a query halfway through, you'll be charged for the amount of data that we've scanned up to that point. The important point here is we're charging for the amount of data that we actually have to scan in order to compute the results. If we have to scan the entirety of your results, of your data set, that's potentially going to be quite expensive. But if you adopt some techniques such as compressing your data, partitioning it, and using a format such as PARQUET or ORC, then the amount of data that we actually have to scan when executing your query can be significantly reduced by orders of magnitude. And that's going to improve the query latencies. We're going to go from potentially several seconds down to just a couple of seconds, but it's also significantly going to reduce the costs of executing those queries. And we'll see an example in a moment how we can drive the costs down from $5 down to effectively just over a cent per query. So I've mentioned several times, and in our example, we're going to be doing exactly this, the opportunity for converting our data to a query-optimized format, such as PARQUET or ORC. So these are storage formats. They're both very similar, and we support both in Athena. They are columnar storage formats, which means that the data on disk is stored in blocks. Within a file, there can be many blocks, and the data within individual blocks is data related to a specific column. So all the data within a particular block is of a homogeneous data type. Okay? So this has some immediate benefits. If the blocks are of a homogeneous data type, it means that we can apply on a block-by-block basis or a column-by-column basis very specific encodings. We can compress within the body of those files on a column-by-column basis. So that significantly reduces the size of these things on disk. Both formats also include a significant amount of metadata describing the contents of those blocks and things such as the min-max values for all of the entries within those blocks. Now this means that we can take advantage of something called predicate pushdown. When we're interrogating these files, we can actually interrogate first of all the metadata and determine which blocks we actually really need to pull off disk. So we don't have to bring the entire file into memory and scan it in order to retrieve that data. Potentially we can identify just portions of those files and stream those into the processor. Okay. So this is by using this query optimized format, using predicate pushdowns, and the fact that a lot of the kind of analytics queries that we're conducting are going to be ones where we're only interrogating specific columns within the set rather than the entire set of columns within any particular table. All these things combined means that we can actually reduce the amount of data that we have to scan in order to compute a result. So here's an example of the pay-per query. So we set up a little test where we had some log data. I think we had a terabyte worth of log data. And that's just in text format. And then we've got this little query up here on the right-hand side where we're doing some aggregations over that log data. So doing some analysis on top of it. If we query via Athena directly against that raw log data, which we're entirely entitled to do, very easy, land that data in S3, start querying. If we do that against the raw log data, we have to scan the entirety of that 1 terabyte of data. So that's effectively going to cost us $5, irrespective of the size of the result set, because we had to scan the entirety of that 1 terabyte. When we converted that to Parquet, we boiled it down to, what does it say here, about 130 gig. So we went from a terabyte down to 130 gig. But because we're now taking advantage of that columnar format, and we're only looking for specific column values within those objects on S3, and because we're taking advantage of predicate pushdown, the amount of data we actually had to scan when we executed the very same query was just over, 2.69 gig. All right? So over 1 terabyte for the first query, just 2.69 gig for the second query. So that reduced our costs down from $5 down to just over a cent for the very same query. And we got the additional benefit that we went from several minutes for the first query to just 5 seconds for the second query. Right? So reduced latencies and reduced costs. In our documentation, we provide several ways in which you can convert your stuff to Parquet or ORC. You can do it through Hive. You can stand up an EMR cluster. Our preferred solution, once Glue becomes available in the regions where you're operating, is to use Glue. It makes it very, very easy to take CSV data and rewrite it as Parquet. All right, we're actually going to finally get down and do some work. So we are going to look at the Athena console. Right, so that was Glue. This is Athena. You can see it looks like a kind of typical SQL client, browser-based SQL client. Top right, we've got the window where we can actually enter our queries, either our DDL to create those table definitions or the actual select statements and so on. We've got a window below that for the result set. Remember, that's being streamed out to us and also written to another location in S3. And then down the left-hand side, we have another view on our data catalog. Now, there's actually one thing to point out here. Athena is already available in Dublin region. So Athena already has a data catalog. When Glue becomes available in the region where Athena is also present, then you can convert from using Athena's data catalog to using Glue's data catalog. So I think over time, we're going to see Glue's data catalog, this highly available account-wide data catalog, being foundational for a lot of these technologies. But even today, you can do a lot of this stuff in Athena in the Dublin region. It has its own catalog. I'm actually running it in US East, so I can take advantage of Glue as well. And I'm already pointed at Glue's data catalog. So we can see here all of the different databases, the very same list of databases that we saw in the Glue console, including my NYC transportation canonical database, which currently has no table definitions. Right? I've actually created some data. I've converted the taxi data and the limo data to Parquet. I've stored that in a bucket in S3, but I haven't created a table definition over it. So that's exactly what I'm going to do now. So here I have several crawlers that I've created. These crawlers are part of Glue. You can create a crawler and then you can schedule it so that crawler can run on a periodic basis. And those crawlers can go looking for sources of data within your AWS estate. They can look for data in S3, and you can point them at Redshift or at a JDBC endpoint, and they can infer the metadata regarding those relational schemas as well, upload all of that into the catalog. So I've got a crawler here, which is pointed at this particular key space within S3. Oh, this is not the crawler we want. It's this one, my canonical crawler, which is pointed at a bucket that I own, where I've actually started outputting some of that PARQUET data. I'm going to run that crawler. Okay. This hopefully is only just going to take a few seconds to run. I'm doing this through the console, but we can schedule the execution of these crawlers. We also have an SDK and a command line tool that also allows you to invoke the crawlers that you've created. So you can create the crawlers through those tools as well, and then you can invoke them through those tools. All right. So it's going to take a few seconds, but effectively it's going away, looking in my bucket in S3. It's discovering some files. If it recognizes the file format, then it's going to open that file and scan the first, I think it might be the first 10,000 rows or so. And it's going to try and apply a classifier to infer the schema for the contents of that file. And we can see here that it's actually added one table to my database. So if I look at my canonical database, I now have a table definition over that PARQUET data. We can see the schema there. And if we flick back to Athena and refresh the view, we now see that we've got my transportation data there as well. All right. So I've created a table definition over my data. I could have done that by creating some DDL here. I can now actually start running some queries. So we've got taxi data and limo data at the moment in our canonical data set. And we can see here the number of entries we've got for each of those. So is that about 10 million rows for the taxi data and just under 1.5 million rows of limo data. I knew there was something else that I wanted to do. Okay, so when Glue actually infers the schema for the stuff that it's found in S3, it's going to create a table definition and it's going to attach specific data types to all those columns. But at the moment, Glue only applies very, very low-level data types. So you'll notice here that my pickup date time and drop-off date time have been identified as big integers. Actually, what I want to do is to convert those to timestamps. In the future, Glue will also infer some of these high-level data types as well. So it will recognize timestamps and will actually add those to the schema definitions. At the moment, we sometimes have to make some of these additional modifications. Okay. So flick back to Athena. What other queries can we run? Okay, we can start running some more interesting analyses. So let's look at some average distances, average prices for some of these taxi and limo journeys. So we can see here that limo journeys are just under 3 miles. That's the average distance. And it's costing around about $10 per mile. Average taxi journeys are just over 4.5 miles. And the cost there, the average cost is about $8 per mile. Okay. And we can get more complex and so on. I've got data in S3. I've created an external table definition. Once that table definition has been created once, it's persisted in the catalog. So you can come back to Athena, find your existing table definitions, and just start writing SQL. So we don't have to go through that entire end-to-end process every time we want to write queries. All right. So the next thing I'm going to do very briefly, the last section, we're actually going to put some visualization on top of this. But whilst we're doing that, I'm also going to be ETLing all of that Uber data into my bucket as well. All right, so I'm going to create a job in Glue. Let's Uber to PARQUET. We have to choose a role because Glue actually has to access some of our resources on our behalf, so we have to supply a role that allows it to do that. With Glue, we can let Glue create for us a script. We can actually upload our own scripts as well. So if you've developed your own PySpark scripts elsewhere, you can actually use Glue to execute those scripts. But we're going to have Glue create for us a script. I need to supply a temporary bucket if there are any intermediate results that are generated. And then I want to find the table that's acting as my source. Okay, so I'm going to take my Uber data, which is in an account that belongs elsewhere, and I'm going to choose a table as a target. All right. So even as we're actually creating this job, Glue is showing us the kind of transformation it's going to execute. And we can actually modify some of these mappings if we so wish. I'm just going to leave that as is for now. There's my job. And what we can actually see here, great. We can actually see that Glue has created for us some PySpark code. Now actually what I can do, if I want, is modify that code further. And that is exactly what I'm going to do here. I'll very briefly tell you what I'm doing. I'm just adding in an additional column which represents the type of data. So we've got limo data, taxi data. So we've got a column in our canonical data set called type with values limo and taxi. For this data set, we're going to add in the value Uber. So all the rows that come from our Uber data will be flagged as or tagged as Uber data. So I'm going to save that and then run that job. Oh, let's just point out this bit here. This line here is a line of PySpark code where we're actually writing to that target, to that S3 target, and here we're specifying the format. And Glue knows already that the data in that target is Parquet, so it didn't even have to ask me. If you create a job and Glue doesn't know what format you're expected to output, it will actually give you a choice. But it's already. All right, so we're going to run that job in the background. Great. So we've got Athena for writing SQL directly against our data, and now we've got QuickSight. So QuickSight is our managed BI and visualization tool. It allows you to create dashboards, create charts, assemble them into dashboards, share those dashboards within groups within your organization. If you want to use QuickSight, you'll have to sign up. You just create an account, and once you've done that, you can access it much as any other AWS service. In order to use QuickSight with Athena, you do need to tell QuickSight that you're prepared to use Athena. So I think there are account permissions here. I've done this already, but I'm just making you aware of it. You need to check this box here that would allow your QuickSight instance to access Athena on your behalf. All right? I've already done all of that. So what I'm going to do is create a new data set. So QuickSight allows me to connect to lots and lots of different sources of data in AWS, to S3, to relational databases in RDS. In this instance, we're going to connect by way of Athena, so we're actually going to delegate a lot of the heavy lifting to Athena and allow Athena to do all the aggregations on our behalf. We can connect to Redshift and so on. In this instance, we're just going to use QuickSight to connect to Athena. And let's call this NYC. So I'm giving a name to my data source. And again, QuickSight is aware of all of the different databases that I could conceivably use through Athena. So we're going to use that canonical one and this particular table. I want to directly query the data via Athena. So QuickSight also has an in-memory computation engine called Spice. It allows you to copy data from all those different sources into AWS into this in-memory computation engine, which can hugely speed up a lot of the kind of visualization queries that you want to run. What we're doing is delegating to Athena in order to be able to scan potentially terabytes or petabytes of data at rest in S3. All right. I'm also going to create a new calculated field. Let's call it hour of day. And we're going to use the extract function. We're going to take the hours within those timestamps from, I think it's the pickup date time. All right. All right, so I've created a connection to a data set. In fact, it's a connection to Athena, which is then pointed at an underlying data set. And as part of that, setting up that data set, I've also created a new calculated field. So I'm going to save that data set and actually then create a visualization on top of it. All right, so let's just have a look at, our data based on the type, limo, taxi. Yep, see at the moment, we've still only got the limo and the taxi data. Our Glue job is still running in the background, converting all that Uber data to Parquet. When it becomes available, once it's actually been output as Parquet in that destination folder, it will be immediately available for querying via QuickSight as well. But at the moment, you can see that we've got far more taxi data than we do have limo data. What are we doing here? So here, ooh. So QuickSight is trying to make sense of your intentions. It's trying to make it as easy as possible for you to create visualizations as quickly as possible. So you notice just by clicking on a few of these different columns here on the left-hand side, we've actually already started to get some visualizations. Now we can tweak them, we can choose the visualization type, we can further modify them. But all I've had to do here is choose pickup date time and the type, taxi or Uber, and already we've got a simple chart here. I've got a slider at the bottom that allows me to scan or to grow and shrink the amount of data that I'm visualizing. I could choose to go all the way down to the hour. And again, we can see here that we can actually expand and contract the range over which we're querying. And whenever we execute one of these queries, or the visualization executes a query, in this instance it's delegating to Athena in order to query against that data sitting at rest in S3. Okay, let's just see if our Glue job has completed. It was this one here, wasn't it? Okay, it's still running. We're 6 minutes in. So there was a bit of spin-up time there in order to provision some of the resources dedicated to servicing our job. Once all that's been spun up, they can be reused for other jobs that we're running within our environment. Under the hood, Glue is also using Spark in order to do these conversions on our behalf. Once that data is output to our target directory, we would actually see our visualizations in QuickSight enriched with that Uber data as well. Okay, that pretty much brings me to the end. I'll take some questions. I know I've already got one question online, which is, can I comment on the difference between Athena and Redshift, or specifically Redshift Spectrum? So earlier this year, we announced a new feature for Redshift for the managed data warehouse. That feature is called Redshift Spectrum. And Spectrum also allows you to query directly against data sitting at rest in S3. Well, that's what Athena allows you to do as well. I think in many ways, these are kind of complementary services. The great thing about Athena is there is nothing to set up whatsoever, other than that external table definition. But remember, you're sharing those definitions across several different services. With Athena, you just start writing queries. So Athena is great for interactive, ad hoc, and exploratory analysis of your data. All right? So again, going back to that Agile Analytics scenario, where we want to conduct experiments, we want to discover something interesting about the data that we have sitting potentially in a data lake. Athena makes it very easy for us to start querying that within a matter of minutes. Redshift Spectrum is a feature that's more appropriate where we're building out, potentially again in an agile fashion, but building out a real data warehousing capability, where we want to analyze our structured data, where we have well understood queries, well understood reports that we want to run regularly against that data. And where potentially we may have very large fact tables, petabytes or even exabytes, sitting at rest in S3, and we want to join that against dimension data that's sitting in Redshift. But it may be in order to identify some of those candidate data sets, in the first instance, we'd go and use Athena. Very quick, very easy to get up and running. We can discover some of those data sets, start writing some exploratory queries, and if we think this is worth productionizing, as it were, we could bring some of those queries into Redshift and take advantage of Redshift Spectrum. But again, Spectrum and Athena and Hive on EMR and Spark on EMR, they can all be pointed at the same underlying table definitions, the same underlying data sitting in S3. Any other questions? I'll take this from the front first.
Quite a detailed question, but let's set up a crawler
Yeah.
to look at some data, change the data type,
Yep.
and then rerun the crawler, and it seemed to overwrite my changes.
Yeah, so the question's around Glue and its crawlers, and the fact that this gentleman, has previously created a crawler and has done exactly what I did after the crawler had run, had changed one of those data types, and then had rerun the crawler, and guess what? Glue changed that data type back. I think that's a feature of Glue today. So the nice thing about Glue is when you rerun those crawlers, if they discover that the sources of data have changed, so it may be that you're crawling JSON data, for example, and in between times you've added new fields, you've modified the structure of some of those sources. Glue will actually version the metadata in the catalog. So what you will see in your catalog is actually some version metadata. But I think unfortunately today when you rerun that crawler, it's going to revert to some of those low-level data types.
So when we saw the Glue data catalog,
Yeah.
we saw some data in S3, but I think you will also have some data which is in like MySQL or something.
Right.
Or at least that's possible, right?
Yeah.
If you're wanting to query across like heterogeneous data sources like that, what are your options there? Like do you have to bring the data into Redshift or something like that?
So the question here is about being able to query across different data sources. In Glue, I can actually point Glue at MySQL or Redshift or other. So I've got relational metadata and metadata regarding files sitting in S3. Can I query across them? I think, well, firstly, Athena itself is today dedicated only to querying data sitting at rest in S3. If we stood up Presto on EMR, that would actually allow us to join, the Presto connectors allow us to join from several different data sources. But typically, one of the strategies that we would employ in terms of building out a kind of data lake platform is to take all of our raw sources of data, including some of that relational data, and create entities within S3 that would allow us to join across those entities. So it may be that we take our raw data and in a separate bucket, as I'm doing in this example, building out some more query-optimized models, and those models may actually take data from several different sources, from relational, from third-party APIs, from other file formats and so on. But once we've built that canonical model, that would allow us to join across those several different sources.
So you mentioned using Python on Glue, PySpark.
Yeah.
So that's supported with Scala.
Yeah, so does Glue today support Scala? Today, no, but it's on the roadmap. Yeah. So under the hood, Glue is running Spark in order to perform those transformations. And as you may know, Spark supports a number of different programming languages. For our first release, we chose Python, but we know that there are many developers who want to use other languages, and that will come. I've got one at the back first, and then I'll...
So I can put my database into our VPC, and I can isolate my S3 to only be accessible from our VPCs. Will this take data out of that framework, out of that document?
So the question is, if I'm isolating my data and only connecting to it, even the data in S3 via my VPC, am I breaking that encapsulation? No, you can set up VPC endpoints when you're configuring Glue so that it can go directly to those VPC endpoints. So the data never has to transit over the internet.
And it won't, as Glue processes it, it won't exit out of the VPC into the Glue or the Athena resources, and then you push back into it.
And yeah, so the other part of the question is, when we're actually provisioning those Glue resources, are they outside the VPC? Do we end up transiting data outside the VPC? My understanding is we provision those resources in your VPC. We create elastic network interfaces within your VPC. They're dedicated only to your account, so nobody else can access that data. There's a forthcoming feature whereby we'll actually encrypt that data whilst it's actually being processed within those resources within your VPC. And that brings me to the end. Catch up with me in the next few minutes or after the next session. The next session is on Glue, but we'll wrap up there. Hopefully that's useful. Thank you.